Hello everyone. In this lecture I shall discuss the modified Euler's method and the improved Euler methods. Okay. So here note that to many authors these two methods are same. Keeping in view the error in both the methods are approximately closer. Right, approximately same. But these two methods are not exactly the same. Okay. I will discuss the details derivation of this to show you minutely the difference between these two methods. Okay. So also in this lecture the detailed derivation and fundamental knowledge are provided. However, for solving the problem just you remember the formula for the corresponding method and apply it in solving the problem. So now if we recall the Euler's method, basically we use it to solve the first order differential equation of this form, right? As you know, the solution curve here is approximated by the tangent line at the initial point of the given interval, right? That means if you have here, this is the solution curve. Suppose this is your solution curve. Already the details discussion are there in the past lecture. So here we have our x0. We just divide it into the nodes. Okay. We divide the x-axis into the different nodes here. This is suppose my here xn and this is my suppose my xn plus 1. You can see refer my previous lecture. Okay. Now as I have told, the Euler's method is approximated by the tangent line. This is the tangent line. Okay. This is the tangent line at the initial point. This is the tangent line. And this is the exact solution. But numerically we are getting this is the approximate solution. You can refer the previous lecture. So we have for the derivation of the Euler's method, we have the equation of the tangent. If I consider the interval, this interval if I consider, then it is the equation of tangent at this point here, okay, is given by this, right? So now here x minus xn, right, but we are approximating at this point. We need to find this yn plus 1. We need to find this is my yn plus 1. We need to find. So this yn plus 1 here is, okay, yn plus 1 here is yn plus fxn yn into this. So we have this is the formula, right? So this is the formula for the Euler's method. You can refer the previous lecture for details, right? That means here this formula is approximated by the tangent line with slope at the initial point of this given interval, right? So subsequently I will discuss the modified Euler method and improved Euler method in details. Before that, let me to introduce myself, Professor Susanta Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, Burla, Odisha, India. So without much delay, let me to discuss the other methods. So you see, in modified method, what we are doing? In modified method, we take a midpoint of this. Suppose you are considering the initial interval. Likewise, we can consider the this interval, final interval xn plus 1. So here this point is, this is equal spacing. It is x0 plus h by 2 point. This is the point. If instead of drawing the tangent at this point, if I draw the tangent at this point, okay, the tangent at this point, then the tangent at this point, then what I am getting? I am getting this y1 is here. I am getting this y1 is here. However, this is the exact, right? And this is the approximate y1 numerically we are getting. And if you compare it, it is this y1 numerical y1 and this y1, this gap here is little less, means it is closer. Somehow it is modified to minimize the error. So here the slope of the tangent, okay, so the slope of the tangent at the initial point is replaced by the slope at the midpoint. Okay, slope at the midpoint here. So now this method is called the modified Euler's method. In fact, you see this. Now if you are considering this, okay, this is a polygon here, and this is the first side of the polygon, right? So this is the first side of the polygon. That's why this method, this modified Euler's method, is also sometimes called the polygon method. Of course, this modified Euler method agrees with the Taylor series of degree 2, means up to h square term. So this is a second order method. This is a second order method. And here Euler's method is a first order method, because in Euler's method, right, in Euler method, it is up to the, if we think of the Taylor series, it is up to the power of h to the power 1 power, means 2 terms. So it is a first order method, okay, as I have pointed out in this previous. Now if you recall this, actually you have to remember this formula only for the Euler's method, okay, with this here n is greater than equal to, n is greater than is equal to 0. So with this initial condition we can solve it. You can refer the previous lecture. So here this Taylor series method agrees, this Euler's method agrees with the Taylor series method of degree 1, means up to the term involving h, which the error is order of h. So it is of first order method, okay. So likewise we can extend this method to your improved Euler method, and however the formula for this is yn plus 1 is yn plus k by 2, where k2 is this. To find k2 we need k1, so I mentioned this k1. You should recall this formula, and as I have told, this is nothing but the tangent line with slope at the midpoint, okay, with the midpoint of this given interval, right? Likewise, what will happen to your improved Euler method? So this modified Euler method is also called the polygon method, right? Modified Euler method is also known as the polygon method. So now coming to the next method, what we call it, the improved Euler method. Improved Euler method. Also this improved Euler method is sometimes known as the Euler-Cauchy method, Euler-Cauchy method, or improved Euler-Cauchy method, or it is Huygens method, because this method is being developed by mathematician Huygens, and also it is also called the RK method, Runge-Kutta method of order 2, what I will discuss in the subsequent lecture, right? So now if you think of this method, this improved Euler method, what happened in this method? So you see, in Euler's method we take the tangent at this point, we take the tangent at this point, okay. Now in midpoint method we take the tangent at the midpoint, but here we take the tangent at the initial point and we take a tangent at this terminal point, okay, at this terminal point. If you take the average of these two tangents, okay, average of the slope of these tangents, okay, if I take this average of slope, okay, average of slope at this point and at this point, so average of the slope at the end points of the interval, okay, then this will reduce to your improved Euler method, okay. So average of the slope, if I am taking this interval for the formula, then I am taking the slope at this point and I am taking the slope at this point and I find the average. So if I take the average, then this average here will be something, this is my y1, this is my y1 by Euler's method, okay. Now if we take the average of these two slope, then this is some point will come over here, right? It is better, it is improved, okay. So the error is less also. Now in many cases it has been observed that, right, this method is closer to this method also. This method is closer to your modified method. So few authors also believe that these two methods are same. However, the little difference is there, okay. If you apply these two methods to a particular problem, we can see the error will vary, okay. So we should interpret these two methods as different, Okay, so now here the detailed derivation I will do it. So this is the equation of the tangent, this is the equation of the tangent, right? And I am taking the average of the slope at the initial point. This is slope at xn, and this is slope at xn plus 1. I am taking the average of these two slope. Okay, so it is y minus yn is slope dy by dx at the point into x minus x, and this is the formula. From this formula we derived it. So you need to remember only, this formula only. Okay, you need to remember only this formula. You have to remember that this is your improved Euler method. Okay, this is your improved Euler method. We have to remember this formula only. Here yn plus 1 is equal to here yn plus k1 plus k2 divided by 2, where k1 is this and here k2 is this. Okay, I will show you the derivation. So here the tangent line with slope is nothing but the average of the slope at the end points of the interval. Okay, now this method also agrees with the Taylor series up to the term h square. You note that this method also agrees with Taylor series up to the second degree term involving h square, with the error is order of h square. Okay, that's why this method is called a second order method. So this improved Euler method is a second order method, and the modified Euler method is also a second order method. Okay, second order method. So I will show you the details of derivation by finding the equation of the tangent subsequently. Now this improved Euler method can be viewed in a different perspective. Okay, because this method is improved from the Euler methods. This is my Euler's method and this is my improved Euler method. Okay, so now combine these two, right? If I combine these two, then we can view in a different perspective, but both the formula are same. Okay, you may use this, or subsequently we have the formula, what is called this Euler predictor-corrector formula. Euler predictor and corrector formula. That means first we use the Euler's formula. Euler's formula is yn plus 1 is yn plus hf xn yn, right? And suppose I say it is my initially at 0th, initially we have my Euler's formula. I call it predictor. I predict it. Now I improve it. How I will modify it? Okay, so I improve it. So in Euler method, this is the slope at the initial point. Okay, I improve it by taking the slope as the average of the initial point and the average slope of the initial point and the terminal point. However, this is improved by this. Okay, instead of simply this yn plus 1, I take this yn plus 1 which is being derived from this previous step. Then again I use the same formula, means I take the average. However, it is my second improvement here. Here we use this one. Okay, this yn plus 1 being used over here, and gradually we go on improving. Okay, and again also I can at third iteration I can improve it again, means I just replace it, means this is my same formula, only thing I am improving this, and I continue this process. Okay, continue this process succeeding, continue this process till these two consecutive approximations coincides. If these two approximations, this answer coincides here, this answer coincides with this answer, okay, then I will stop here. Okay, I will stop here. That means if I continue in this way, I can find again yn plus 1 fourth. So you see that the succeeding approximation is better, means this is better than this previous, right, and better than the preceding ones, and are called the corrected or improved values. Okay, So now we continue this till the successive approximation coincides. If two successive approximation coincides, okay. So this Euler's method, this is my Euler's method, this is my improved Euler methods. So jointly they are called the Euler's predictor and corrector formula, because it is predictor and it is my corrector. Okay, it is my corrector. It is corrector. Corrector means it is corrected. So what we call it? Improved Euler method or corrector method. Okay, it is corrected here. So that's why it is also known as Euler's predictor and corrector formula. Right? Euler's predictor and corrector formula. However, this version is same thing as this formula of the simply improved Euler method, as we see. Okay, as you see, means this formula is equivalent to, that's why I write it or. So this formula is equivalent to this. Okay, so better we should use it, right? So once we solve this problem, then your idea will clear. So don't be confused. To have a better understanding of this entire theory, avoiding all the confusions, so let me to derive the formulas. So let me to derive the formula for the Euler methods. As I have told you, the Euler's method is approximated by the tangent line at the initial point. Suppose I am taking the tangent at this point. Okay, I am taking the tangent, and the equation of the tangent here is equation of the tangent, and this gap is your h. Okay, this is your h, this is equispace, this is all h. Okay, so initially I find in this interval. So here equation of tangent is y minus y0 is dy by dx at the initial point, at this initial point, and here it is x minus x0. This is at x0 y0. So this is nothing but f of x0 y0 into x minus x0. Okay, I need to approximate the solution here. So I need to find y1. So my y is equal to here y0 plus x minus x0 into f of x0 y0. Now you see, I want to find the solution here. I want to find y1. So at x is equal to x0 plus h means my x1. So what is my x minus x0? X minus x0 is my h. Okay, so this x minus x0 is my h. So my this y1 becomes, now it is y1 becomes is here y0 plus hf x0 y0. Okay, y1. So if I continue it to get here yn plus 1, the generalized formula is yn plus hf xn yn. So this is the formula for the Euler's method, n greater than is equal to 0. Subsequently, I have my modified Euler method. So in modified Euler method, what we will do? This gap is h. Okay, this gap is h. This gap is h. This gap is h. Everything is h. Okay. So here now I take this midpoint of this. So this point will be my x0 plus h by 2, and at the corresponding point with y0. Okay. So I have to draw the tangent at this point. I have to draw the tangent at this point. So this is my y1. This is my y1 here. I want to find this y1 here. Okay. So by Euler's method, this y1 is given by the formula. It is y0 plus hf x0 y0. But I want to replace this. Okay. I want to replace this. Replace by the slope at your x0 plus h by 2. x0 plus h by 2 corresponding to this will be your f of x0 plus h by 2. I write it, it is x0 y0, sorry. This point is your x0 y0. Likewise, this point will be x0 is replaced by this, and y0 is replaced by this. Okay. So now in view of the Euler's formula, as you know what is Euler's formula? y1 is y0 plus hf x0 y0. But here we are taking h by 2. So this will be modified as here y0 plus h by 2 x0 y0. So I substitute it here. So this will be y0 plus hf x0 plus h by 2. Now in view of the Euler's formula, it will be here y0 plus hf x0 y0. Okay. So this is my formula. This is h by 2. This is h by 2. Okay. Now if I set k1 is equal to hf x0 y0, then this term will be my k1 by 2. This term will be my k1 by 2, and then I write this will be y0 plus hf x0 plus h by 2 y0 plus k1 by 2. Okay. Now if I denote this entire thing as k2, then I can write it is yn plus k2. Okay. So what is the necessary formula? Therefore the formula for modified Euler method is given by, you see now it is y0. Now subsequently I will extend up to yn plus 1. So I write it here. Subsequently the formula is here yn plus 1 is yn plus k2 with here k2 is equal to here k2 is equal to as I have told you, it is hf xn plus h by 2 yn plus k1 by 2 with k1 is equal to, I need k1 with k1 is equal to hf xn yn. So this is the formula for the modified Euler method. Okay, modified Euler method, or what we call this polygon method. Okay. Now let us derive the formula for improved Euler method. So in improved Euler method, what we are doing? We are taking the average of the slope here. Okay. So this is the tangent at this point. This is the tangent at this point. Right. Now if I take the average slope of this 2, then this average slope of the 2 will be somewhere, it will be somewhere like this. The average slope of this 2, it will be somewhere like this. Okay. So now this will be a y1, right? So now the equation of the tangent here is y minus, this gap is h, this gap is h, this gap is h, this gap is h, y minus y0 is equal to the slope here is, I am taking the half of the average slope at this point f x0 y0 plus slope at this point, it is f of x1 y1. Okay, I am taking this into x minus x0, but I need to find y1 here, approximate y1 here. So at my x is equal to x1. So now at x is equal to x1, what will happen? This becomes your y1 is equal to y0 plus, so here x1 is here x0 plus h, so this gaps becomes here h, so it becomes, this is bringing to this side, here h by 2, here f of x0 y0 plus f of x1 y1. Now in view of this Euler's method, okay, if I in view of this Euler method, what is y1? y1 is equal to y0 plus hf x0 y0. So if I substitute it, I am getting y0 plus h by 2 f of x0 y0 plus f of, this is your x1, or or x1 can be written at x0 plus h, and here y1 here is replaced by y0 plus hf x0 y0. Okay, if I continue in this way, my yn plus 1 will be, if I continue in this way, my yn plus 1 will be yn plus h by 2 f of xn yn plus f xn plus h, here yn plus hf xn yn. Now if I set this is as k1, okay, if I set this is as k1, I can write it is yn plus h by 2 f of xn yn plus h plus f xn plus h yn plus k1. Okay, yn plus k1. So I can write it now. Here this is yn plus, I take 1 by 2 here, bringing h inside, it is hf xn yn plus f hf xn plus h yn plus k1. Okay, so now if I denote this as my k2, okay, this is your k1, this is your k1. Now if I denote this as k2, then this formula will be, here yn plus half k1 plus k2. So in simplified form I can write the formula as thus the formula for improved Euler method is given by here yn plus 1 is equal to yn plus half k1 plus k2, where k1 is equal to hf xn yn, k2 is equal to hf xn plus h, and yn plus k1. So this k1 is taken from this. Okay, so this is the necessary formula with here n greater than equal to 0. Subsequently for n is equal to 0 I find y1, that means I can find y of 1, y of x1 I can find, y of x2 I can find, and I continue it as in the given interval. Okay, so this is the necessary formula, we have to remember it. And this method is also otherwise called as, this formula is also otherwise called as RK method, Runge-Kutta method of order 2. Also it is called as Huygens method, right? It is developed by Huygens, or it is called as Euler-Cauchy method, right? Euler-Cauchy method, and it also agrees with Taylor series up to h square, right? So this is a order 2 method, right? And the error here is order of h square, and error here is epsilon is here order of h square. So this is a second order method, Runge-Kutta method of order 2, right? So this formula in an alternative approach, right? What we call OR, we may use this or that, and this alternative approach here is called as known as the predictor-corrector method, Euler's predictor and corrector method, and this formula can be written like this. Here yn plus 1 is equal to yn plus hf xn yn. This is in view of the Euler's formula, right? What we call as the predictor, and you say suppose it is at this 0th step, at the initial stage we have this. Now we improve it. Okay, we improve it. How we improve it? Here y n plus 1 by the improved method. You know the formula. By the improved method, you know the formula. This is the formula. So this is the formula. You improve it. So you improve it. This is my initial formula. So you improve it by using this. You improve it by using this. Where this yn, it will come from the Euler's method. It will come from the Euler method, or it will be seen as yn 0. Okay. So this will be given by, this is given by, improve it, yn plus 1 is equal to here y0 plus h by 2, as I have told that the average of the slope, it is f of x0 y0 plus f of x1 means x0 plus h. So I write it x1, it is here y1. Okay, this is your y1. So I take n. I am taking n here. It is f of xn yn plus f of xn plus 1 and yn plus 1, and this yn plus 1. Okay, this yn plus 1 will be taken from this, so I write it 0. Okay, now again I further improve it. And let me to write it. So this is first improvement, and again I further improved it, yn plus 1, the second improvement here. The second improvement here is, the formula is here the same. Here y0 means yn, this is yn plus h by 2 f of xn yn plus f of xn plus 1 and yn plus 1. So this yn plus 1 is a further improvement from this. Okay, this. Then again I further improve it. It is my yn plus 1. Third improvement here is yn plus h by 2 f of the same formula xn yn plus f of xn plus 1 and this yn plus 1, and this improvement here is taken from this, right? And you continue from this. You continue till two consecutive approximation coincide means you have here, this is say answer 1, you have here answer 2. If these two are coincides, okay, are coinciding, right, means we continue this. However here yn plus 1 at k plus 1th correction is a better estimate than yn plus 1 at the kth estimate, means subsequently this we improve. This is the improvement of this, and this is the improvement of this. So the subsequent approximations are better, but consequently where we are going to stop, these two consecutive approximations are same. Okay, so this is what, so means we may use this, or we may use this, so this is obviously better. This is the improved Euler methods. So let us see some worked examples to find the difference between these methods. So now coming to the solved example 1, you are asked to solve this with the initial conditions, and you have to find y of 0.2 and 0.4 by modified Euler method and by improved Euler method, and we see the difference, and we also estimate the error in each case by comparing the actual solution. Coming to the actual solution, so your dy by y square is minus 2x dx. If you integrate it, minus of 1 by y is here minus of x square. Let I take the constant minus of c. So my y is equal to 1 by x square plus c. Okay, now y of 0 is equal to my 1. So therefore my 1 is equal to 1 by c, implies c is equal to 1. I substitute the value of c here. So this implies my y is equal to 1 by x square plus 1. So this is my actual solution, or I write that y of x is equal to, okay, y of x is equal to I write. So this is my actual solution. Now I find the solution by your modified Euler method. So what is the formula? yn plus 1 is equal to yn plus k2, where k1 is equal to hf xn yn and k2 is equal to hf xn plus h by 2 yn plus k1 by 2. Okay, so I start from 0. So the interval here is 0. I start from 0. Okay, I start from 0. So I have to reach at 0.4. Okay, 0.4. So I have to take the h. Suppose I take h is equal to 0.2. Okay, so let my step 1 for n is equal to 0. Okay, what is your k1? N is equal to 0. Let h is equal to my 0.2. So x0 is given 0, implies x1 is 0.2, x2 is my 0.4, and y1 is given my y1, y0 is given my 1. So at step 1, this is my step 1. At my step 1, here k1 is equal to hf x0 y0. So this is equal to h x0 y0 is here minus 2x0 y0 square is minus 2x0 y0 square. So I substitute the value. H is my 0.2 into minus 2 into x0 is my 0 and y0 square. So this is equal to my 0. Now my k2 is equal to hf x0 plus h by 2 y0 plus k1 by 2. So this is equal to hf x0 plus h by 2. It is y0 because k1. So this is equal to h into minus 2 into here x0 plus h, x0 is here 0 plus h by 2 plus into y0 square into here y0 square. If you substitute it, it is 0.2 into here minus of this is h, simply h is my 0.2 into 1 square. Okay, so this is minus 0.04. So therefore what is your y1? Y1 is y of 0.2. So this is equal to y0 plus k2. Okay, y0 is, so this is 1 minus 0.04 is 0.96. So my y1 is 0.96. Subsequently I find y2. So in step 2 I simplify it to get my k1 is equal to minus 0.073728. Similarly I solve my k2. K2 is minus 1.10262. So my this is y1 plus k1. Okay, y1 is this. So my 0.96 minus 1.10262. So I am getting 0.857738. So this is my y of 0.4 I am getting, y of 0.4 I am getting, and my y of 0.1. So we just compare after we get the solution by improved Euler method. So likewise I have already taken that let h is 0.2. So my step 1, what is my k1 I find? So my k1 is hf x1 y1. yn already I got it, y1 here. Sorry, it is x0 y0. So this is equal to h into, in view of this, it is minus 2 x0 y0 square. The value of x0 is 0. So this is equal to 0. And what is your k2 is hf. Here x1 means xn x0 plus h y0 plus k1. So this is equal to hf. It is x1, it is y0 because k1 is 0. So this is equal to here 0.2 into minus of 2 into x1 into y1 square, y0 square. Okay, So this is equal to 0.2 into minus of 2 x1. x1 is my 0.2 square, 0.04 into y0. y0 is my 1 square. So if I simplify it, I am getting, so here k2 is this. If you simplify it, is minus 0.08. So therefore y of 1 is, y of 0.2 is y0 plus k1 plus k2 by 2. y0 is here 1 plus k1 is 0 and it is minus 0.08 by 2, and if you simplify it, it will be at 0.96. It will be at 0.96. It coincides with this previous one. It coincides with your this. Now coming to y2 here. Step 2. In step 2, so if here n is equal to here 1 here, and here in this step n is equal to here 0 here. Okay, so here my k1 is h minus 2 into x1 y1 square. So h is my 0.2 into minus 2 into x1 is 0.2, y1 is 0.96 square. Okay, if I simplify it, I am getting this k1 is minus 0.073728. Similarly, if I simplify it, it is minus 0.125676. So I have, this is the formula here. So y1 value I substitute 0.96, and this is k1 plus k2 by 2. So it is minus of 0.073728, and it is minus of, it is half, minus of 0.125676. If I simplify it, it will be my 0.860298. Okay, you see it if you compare with this previous method here, and there is a little difference here. Okay, little difference here. So let us now compare the error here. Now if you compare the error by actual solutions, this is y of 0.2 is this, because we got y is equal to what? 1 by 1 plus x square. Okay, putting x is equal to 0.2, this is my a. Now by modified Euler method, we already got it. By improved Euler method, we got it at 0.2. Okay, both are same. So however, the error here is here 0. Here error is actual minus numerical. So this is a minus b. I take absolute value in order to avoid the negative sign. So it is 0.001538, and here also the error is same. So if the error at 0.2, here is your actual a minus this numerical by c. By to avoid this, I take the absolute value. So I am getting the same error because these are same. So it is my 0.001538. Okay, 38. However, in case of this at level 0.4, and this error is here e minus f more absolute value. So I am getting this error is 0.004331, and here it is actual e minus numerical by improved Euler method g, absolute value I am taking. So this is I am getting 0.001771. Okay, so you see here these two errors are not same. However, this is smaller than, this is suppose my m and this is suppose my n. Okay, so I am getting the error by this n is smaller than m, right? n is smaller than m I am getting. So improved Euler method giving us the less error, right? So here what we conclude, improved Euler method, right? Improved Euler method gives the better estimate than the your modified Euler method. So what is our remark? For x is equal to 0.4, improved Euler method is better, is a better estimate than your modified Euler method. Okay, now let us discuss one more example. Example 2. Given dy by dx is x square plus y, initial condition y0 is equal to 1, take step length h is equal to 0.05, find y of 0.05 and y of 0.1, means 2 steps are needed. So here we have to first solve it by modified Euler method, then we solve it by improved Euler method. In fact, this improved Euler method and the Euler predictor and corrector method both are same, both are the same. Okay, same, but from this perspective we will also see this answer and we will find this answer. Okay, so let us discuss the details of the solution. Now coming to the solution. So from the perspectives of modified Euler method, we have yn plus 1 is equal to yn plus k2, where we need some k1 in k2, so k1 is hf xn yn and k2 is hf xn plus h by 2 yn plus k1 by 2. So this is the formula by this modified Euler's method. So here n greater than equal to 0. Okay, we are given f of xy is x square plus y, x0 is 0, y0 is 1, h is 0.05, so your x1 is 0.05 and x2 is next improvement is 0.1. So we need 2 steps. So at step 1 k1 is equal to hf x0 y0. So here n is equal to 0 I am taking. So this is equal to, if you solve it, it is h into your x0 square plus y0. So this is equal to h is 0.05 into x0 square, 0 square plus 1 square is here 0.05. Now we 5k2 is hf x0 plus h by 2 y0 plus k1 by 2. Okay, and if you simplify it, it will be 0.0513. So for k2 the details calculation is here, it is 0513. Now as you know, y of 1 is y of 0.5 is y0 plus k2, so this much. Now coming to step 2, it is putting n is equal to 1, k1 is hf x1 y1, x1 value is 0.05 and y1 we got it, so we substitute it and you simplify it to get. Similarly k2 is hf x1 plus h by 2, y1 plus k1 by 2, this k1 by 2, k1 is here, k1 by 2, if I simplify it, it will be here this. So now here y2 means y at 0.1 is this much. Okay, so now coming to the improved Euler method or the Huygens method or what we call the Runge-Kutta method. So here the necessary formula is yn plus 1 is yn plus k1 plus k2 by 2, where k1 is this and k2 is this. As you know, fxy is this, x0 0, y0 1 given, we select, or h is equal to 0.05 is also given. So with the increment of h it is this, with next increment it is this. So at step 1 here k1 is equal to hf x0 y0. So fxy is x0 square plus y. So it is 0.05 x0 square 0 square plus 1. Okay, so it is here 0.05 and k2 is hf x0 plus h y0 plus k1. So if you simplify it, you will get hf 0.05 plus 1.05. 0.05. So this will be 0.05 into 0.05 square plus 1.05. So this is equal to 0.052625, and therefore here y of x1 is y of 0.05 by this method is here y0 plus your k2, y0 plus your k2, k2 plus k1 divided by 2. So y0 is here 1 plus this by 2, k1 plus k2 by 2, and your k1 is 0.05 plus 0.052625 divided by 2. If I simplify it, it will be 0. It will be here 1 point. It will be here 1.051325. If you take it up to 4 decimal places, it is 1.0513. Okay, so you see this k1, this y1 agrees with this y1 also, right? Now coming to my step 2 here. Step 2 here I am taking n is equal to 1. So what is k1? K1 is hf x1 y1, and k2 is hf x1 plus h, and here y1 plus k1. So what is your hf x1 y1 is your hf 0.05 and y1 is here 1.0513. okay, and if I simplify it, it is h into x1 square plus y1, and if you simplify it, it will be my 0.05269, and if I simplify it, it will be my hf 0.1 and 1.10399. so if I multiply h into 0.1 square plus 1.10399, and if you simplify, you will get it 0.0556995. so therefore your y2 is y of 0.1. so this is equal to y1 plus k1 plus k2 by 2, and here y1 is here 1.0513 plus k1 plus k2 by 2 half. Here k1 is 0.05269 plus here k2 is 0.0556995. if you simplify it, it will be here 1.10549. if you round it up to 4 decimal point, 1.1055. okay, so you see this formula also agrees with this formula is also agrees with the earlier method 1.1055, right? So here this both the methods, modified Euler's method and improved Euler methods in this case, are getting almost the same answer up to the 4 decimal places. Now this B, okay, improved Euler method, if you think it in the sense of the predictor and corrector method, alternative or B means it is your predictor, improved Euler method, or what we call it predictor-corrector method. Then we have the following aspects. You have what is the formula here? Here yn plus 1 is equal to yn plus hf xn yn. It is in the sense of the Euler's method. Okay, n greater than equal to 0. N greater than is equal to 0. So now it is at the initial stage. Now I improve this. Here yn plus 1 is, okay, I improve it. First correction is here yn plus half this average of the slopes I am taking. Okay, it is f of xn yn plus it is f of xn plus 1, and it is yn plus 1, and this yn plus 1 means this I have to take, and subsequently I have yn plus 1. The second correction here is the same thing, yn plus h by 2 f of xn yn plus HF xn plus 1 and yn plus 1. This correction I have to take, this correction I have to take, this correction I have to take, okay, this correction I have to take, and I continue it. So at step 1 I am getting, so now we have fxy is this, x0 given, y0 given, h we have taken, so x1 improved this, and x2 the next. So here at step 1 we have this formula in view of the Euler's formula. So substituting the value of y0 x0, this I am getting 1.05. now I improve it, y1 at 1th iterations, it will be y0 plus h by 2 f of x0 y0 plus f of x1, and it is y1, this y1 I am taking, 0 I am taking, okay. So now I simplify it, so this is equal to, I am simplifying, 1 plus 0.05 by 2, it is here 1 plus x1 is 0.05 square plus here 1.05, and this I am getting 1.0513. so the next corrector here, the next correction here is my y1 of 2, y1 in the second correction here. So this will be equal to my, it is y0 plus h by 2 f of x0 y0 plus f of x1 y1, and this y1 should be this, okay, y1 1, right, y1 1. So I solve it, so this will give you 1 plus 0.05 by 2, it is 1.0025 plus 1.0513. so I am simplifying it to get 1.0513. you see, since this and this coincides, we cannot go further, and we say that y of 0.05 is here 1.0513. now at steps 2, so here y2 will be this, so this will be the value of y1 is this much, we substitute it here, and I simplify to get it 1.104. so it is at the 0th step. Now this value will be substituted here, and now this is at the first correction, and this is the second correction, so I write here the first correction, okay. So I substitute this value here, and I simplify it to get this 1.1055. Similarly this value I substitute, right, similarly this value I substitute, here, okay, I substitute here, and this will be my 1.1055. you see, since the answer at 2 consecutive steps coincides, okay, this and this coincides here, so therefore we stop it here. So therefore here y2 is equal to y of 0.1, right, is equal to here 1.1055, okay, 1055. so you see here y2 in this method, y2 also coincides with this previous method, okay. So here we are getting all these results are same by any of the methods, okay. So at this stage I should conclude it. So to conclude, the improved Euler method is different from the modified Euler method. Improved Euler method is also called Huygens method or Euler-Cauchy method or RK method of order 2, whereas modified Euler method is a polygon method, okay. As we see in example 1, both are different. Moreover, here simple Euler method is nothing but RK method of order 1, Runge-Kutta method of order 1, and here improved Euler method is RK method of order 2. So in the upcoming lecture we will discuss the Runge-Kutta methods of all orders comparing this lecture. This lecture is lengthy to make you understand everything starting from the basic difference, okay. So the video is getting lengthy, we should close it. Thank you all, and you should like and subscribe to this channel. Like and subscribe if you find the benefits out of this lecture. Thank you all. Have a nice day.